Thank
Thank
you,
you.
sir. Thank you for accepting our invitation and delivering the talk on the rings and graphs. Thank you very much, sir.
Well, I thank you. Uh, Here is the definition of the zero divisor graph of a ring. Uh, this is, classical definition where you have your commutative ring R and you take here the ZR star is equal the set of all zero divisor of the ring, but you remove zero. And how you connect two vertices. Two vertices connected by an edge if and only if when you multiply them you get zero. And here is a remark about this definition. This started in 1988 in this paper by Bach, but in this paper uh, he was interested in coloring the vertices of the ring. And in that paper, he considered all elements of the ring to be the vertices. I'm looking at number one. Number one, uh, there, the vertices are all element of the ring R, and he was interested in coloring. In number two, the authors in number two, they continue the work in number one and they answer some questions raised in number one. The definition of the zero divisor graph as we know it now, and we many study it, started in 1999 by number three, Anderson and Livingston, where they introduced what we call now the classical zero divisor graph. So the classical zero divisor graph or the divisor graph of a commutative ring, you have your set of vertices are the non-zero zero element of the ring, zero divisor element of the ring, non-zero zero divisor element of the ring, and two vertices connected by an edge if and only if when you multiply them you get zero. Okay, here are some of the, okay, it's known, it's not written here, but I mention it. It's known that the zero divisor graph is always connected. Okay? And we don't study loops when we study zero divisor graph, and it is symbol that means there is no multiple edges. If two vertices connected by an edge, there will be only one and only one edge. So multiple edges are not allowed, loops not allowed, even though later on other maybe consider that where they allow loops. And what I mean, how you get a loop, like if you have an element in the ring where x squared equals 0, if you have nilpotent element, then you can map x to itself like a loop. But in the zero divisor graph, as we all know it, loops are not allowed. Okay? Simple undirected graph, and the graph is always connected. Okay, here is the things that will be of interest when you study the graph. I want to know, like, here is the first question. Let D be a connected symbol graph with vertex set at V. And you allow the number of vertices to be less or equal to 3. In fact, if I give you a minute, you draw all of them. There will be, uh, you know, uh, maybe. So the question is, can we find a ring R such that the zero divisor gamma here is not written in the, I'm using gamma all the time. But remember, gamma, it means the zero divisor graph of the ring equal to D. And the answer is yes. How? The answer is yes. Okay, and the same question, I let D be a connected symbol graph with vertex set V, where the number of vertices equal 4. I just went up with one vertex. Can we find a ring R where the zero divisor graph is equal to the given graph? Okay? All right. You and me, okay, here is the answer to this question. The answer to these questions, like here I have a graph with only one vertex. Okay? Only one. What are the rings, non-isomorphic rings, that will have this graph? There is only up to isomorphism, only two. So I have up to isomorphic two rings, Z4, and the polynomial ring with coefficient from Z2 mod the ideal generated by x squared. If you take the zero divisor of this ring or this ring, let me maybe make it a little bit smaller. Okay. All right. Is that okay now, or I should keep it as
Yes,
it?
sir. Okay, sir.
Okay.
Thank you, sir.
So, all right. What about if I have two, like two vertices? Here is one, and here is one. They are not written, the vertices here. So I have this graph. Then I will have these rings. These are not isomorphic. Z9, Z2 cross Z2, the polynomial ring with coefficient from Z3 mod x squared. The zero divisor graph of each one of them will give me this. Okay? And what about this one here? Here we have a triangle, three vertices. So what are the rings? Again, these are the rings. He gave you, so these are non-isomorphic ring, but they gave you the same graph with three vertices. Okay? That's, like a good question. And from there, we conclude few things, like, as I mentioned, like this ring, Z4, definitely is not isomorphic to this ring, Z2 x mod x squared. They are not isomorphic, but the graph for each one of them is the same. So the graph are isomorphic. The zero divisor graph is isomorphic. Does it mean the two rings are isomorphic? So the answer definitely is no. These three rings I have here, they give you this graph. But definitely the rings are not isomorphic. And the same thing, here is an interesting for order 4. So here I have a graph, symbol, undirected graph, three graph. Look at them. of order 4. That means I have each graph has 4 vertices. 1, 2, 3, 4, 1, 2, 1, 2. There is no vertex in the middle. There is no vertex in the middle. So you have also 4 vertices for the last one on the right. Okay? If you try to sketch like all the graphs with 4 vertices, simple, undirected, connected, maybe you will find 6 of them. Only these 3 where I can find rings where the zero divisor graph give me the given graph. So I believe there are about 6 simple connected undirected graph with 4 vertices. Out of these 6, only these 3 that correspond to a zero divisor a graph of some ring. Like this graph, the last one, correspond to 2 non-isomorphic ring. Z25, the polynomial ring with coefficient from Z5 mod x square. The zero divisor graph of this ring will give you this shape. And the zero divisor graph of Z25 also will give you the same shape. For the square or rectangle, there is only one ring that will give you that, up to isomorphic. Okay? And for this shape, you have only one ring. Okay? All right. Okay, so in here I made a remark, and maybe this is here I have to mention something for a student who looking for a project and for a student who like to use computer and math together, that you can still do some investigation about this kind of a question, because I'm not sure, maybe up to 20 like rings, a graph with vertices up to 20 or 30, they were able to classify uh, the corresponding rings for the given graph. So the you give me a graph, and then I should tell you if I have a zero divisor graph that will give me what you gave me, or I can tell you no, there is no such ring where the zero divisor graph will be the graph you gave me. This kind of work started in 2007 by Redmond, and he published 2 papers in the same journal, and I think maybe in the second one he corrected some error in the first one. And he classify, I believe, up to 14. I don't remember. Like if you have a graph with that many vertices, what can I say about the zero divisor graph? And if there is a zero divisor graph that correspond to the given graph, can you tell me what are the rings? And this is kind of very good question. And that's what makes the subject more interesting. Okay, here I'm gonna share with you what he did briefly. I will explain that. Okay, so you start with, I gave you that. If you have a graph with one vertex, okay, this will be like complete graph with one vertex. Boring. So how many elements will be in the ring? There will be 4. You see the table, vertices, and then you have a ring. What is the ring? What is how many elements in the ring? And what kind of graph you get? For one vertex, these are the rings that will give you a graph with one vertex. What about a graph with two vertices? Up to isomorphic again, these are the rings that will give you a graph with two vertices, and the shape of the graph you're gonna give me has to be K2, of course. Okay? What about if I move to three vertices? If you have a graph with the three vertices, okay? And this is kind of interesting, maybe. Okay? So, if you could have a graph with the three vertices K12, what I mean with K12, all of you know K12 means a complete bipartite graph, meaning your set of vertices will be can be split into two set where two vertices are connected by an edge if and only if they belong to two different vertex set. So in the street language, if I want to explain complete bipartite graph, that means your vertices will split into two sets. Let's call them A and B. Every two vertices in A are not connected by an edge. Every two vertices in B are not connected by an edge. Every vertex in A is connected to every vertex in B by an edge. Okay? So you know how the shape of K12. So you see that here, that all, like if you have a graph symbol connected, a graph with connected with the three vertices, these are the possible shapes for the graph. And for all of them, K12 or K3, there is no other symbol connected graph other than K12 or K3. So for a graph with the three vertices, yes, we can find rings where the zero divisor graph of the ring will give you K12. Like if I take Z8, the ring Z8, if you calculate the non-zero zero divisors of Z8, it will be 2, 4, 6, three vertices. The graph is going to look like K12. Okay, so here he classify up to isomorphic all rings that will give you such a graph with three vertices. Let's move to a graph with four vertices. With four vertices, there are some graphs that are not mentioned. So like here I have K13, K22, K4. Well, K4, right? What about C4? C4, a cycle with four vertices. A cycle with four vertices. Yeah, that will be, I think, K22 maybe. That's a cycle with four vertices. But you can construct, what about four vertices and you have a diagonal in the middle? Like you connect two vertices. I think this graph will not be K13 will not K22, will not be K4. So you have a square or a rectangle, and then you have a diagonal. That's still a graph with 4 vertices. The question, can we find a ring where the zero divisor graph of the ring is the given graph? The answer is no, because as I told you, I think there are 6 different graph connected with 4 vertices, but only 3 of them can be realized as zero divisor graph of some rings. Okay? And you continue, you get the idea, and that's where your work, if you are a student, and of course they use computer here, and we're living in a century where we have high-speed computers, and they can do all these fancy calculation, of course. So maybe with the help with computer, you can increase the number of known rings with for a graph with 100 or 200 vertices. I don't know. And you can answer the question when we can have zero divisor graph equal to the given graph or not. The same thing for 5. As you notice, for number 5, if you have a graph with 5 vertices, then you can have rings that give you K14. And there is only one ring, the integer modulo 2 product the integer modulo 5. This ring, the zero divisor of this ring will give you that. Okay? And you could have K23, complete bipartite graph, and this will be the ring. Or up to isomorphic, there is only one. And that's kind of interesting. And then for this is the figure I think I included down. Yeah. Like here, you see this figure? This is a graph with 1, 2, 3, 4, 5. For this kind of a graph, yes, I do have rings where the zero divisor of the graph give me this. And the same thing for 6. 1, 2, 3, 4, 5, 6. Okay? Here I have. Anyway, so you get the idea what they did. And these stop, as I told you, up to 14. But we know, and you know, and I know, like if you look at 14, there are more graph with 14 vertices. Many more. But only these are the graph here. 1, 2, 3, 4, 5. There are, out of these many symbol connected graph with 14 vertices, there is only 1, 2, 3, 4, 5, 6 non-isomorphic, different graph with 14 vertices, and these are the rings. All these rings here, the zero divisor graph will give you the corresponding graph. But I think this list increase up to 20, but don't take me for that. So maybe you can, investigate that and, continue this kind of work. I think it will be interesting. Okay. All right. So we go back to this thing, the talk again. I give you some properties. Like this is in the same paper I mentioned that if your ring is finite and the number of the vertices of the zero divisor graph bigger or equal 4, then the zero divisor graph is a star graph if and only if your ring look like that. So here's this is what I try to tell you, like how you make connection between a graph and the structure of the ring. If your ring is finite and a star graph, then your ring should look like that, where F can be any field. And what you conclude from that if the zero divisor graph of the ring is a star, then how many vertices are in the zero divisor graph? Remember, the number of the vertices will be the number of the non-zero zero divisor element of the ring. It will be always p to the n for some prime p. And kind of interesting, related to what I just told you, if you have a star graph, the way you write a star graph is k1, comma 4 or k1, comma n. It will be a complete bipartite, and your vertex set consists of two sets, A and B. In A, there will be only one vertex, and in B, there will be the remaining one. And the vertex in A will be connected to every vertex in B, and every two vertices in B are not connected. So if you have this kind of a star graph, then yes, look at the answer. Every star graph can be realized as what? Zero divisor graph of some ring. So that's it. If you give me K1 1 million, then I should be able to give you the ring that will give me that number. Wow. But don't get me that. I'm wrong what I told you. There is restriction. The your graph shouldn't have exactly b to the n element. Sorry about that. So it's not in general. Star graph of order b to the n. Okay, let's move to a symbol regular graph. What do I mean with regular graph? That means you have a symbol connected graph, and the degree, all vertices have the same degree. So like, K4, comma 4, complete bipartite, where your vertex set is split into two sets, A and B, where the cardinality of A equal to the cardinality of B. Here are the examples of regular graph. KNN, complete bipartite graph. KM, the complete graph. CN, where is n bigger or equal to 3. There are many graphs that are regular. Many. You can sketch many graphs. So the question is, here is the question. When the zero divisor graph of a ring is regular? The answer was given by Saeed Akbari and Mohammadian. They are two Iranian mathematicians. In fact, the first one, he has many fingerprints in a graph attached to rings. He has many contributions to this field, the one I'm talking about. In many graphs, but in particular the zero divisor graph. In this paper, 2004, he said, let R be a finite commutative ring. If the zero divisor graph is a regular graph, then it has to be either complete or KNN. That's it. You cannot have any other shape, period. As I told you, there are many regular graphs. So if the zero divisor graph is regular, then it has to be either complete or complete bipartite. And he gave the shape, how they should look like. Like I have, uh, cycle with 5 vertices. A cycle with 5 vertices, I cannot have a ring where the zero divisor graph will be the cycle with 5 vertices. But you know, a cycle with 5 vertices is regular. The degree of each vertex will be 2, right? Okay. All right, what I mean, I mentioned that what I mean with connected graph. Connected, as you know that you can walk from one vertex to another by a path. The girth, what is the girth of the graph? Is the length of a shortest cycle. And if there is no cycle, then we say the girth is infinity. So what do we mean with girth infinity? It means there is no cycle in the graph. No cycle in the graph means the girth is infinity. Okay? There is one theorem, it seems, yeah, here we go. I have to, before I give you this theorem by Mollet in 2002. Remember, the first paper was in 1999. Anderson and Livingston, they prove that the girth has to be less or equal 7. And they were able to give examples for a graph, zero divisor graph with girth 3 for infinity. But they were not able to give examples of zero divisor graph of girth 5 or 6 or 7. But they have the theorem say, if you read that theorem in the paper by Anderson and Livingston, that the girth is always less or equal 7. However, in 2002, Mollet, he gave a complete answer for the zero divisor graph, that the girth can be a triangle or square, or there is no cycle. Infinity mean the graph has no cycles, like trees, All right? So we have a complete answer for this. For the girth, what is the shortest cycle, the length of the shortest cycle in? All right. Here is a nice result by Anderson and Mollet. Remember, Mollet answered the question in 2002. Anderson is the first author on zero divisor graph. Both of them, they wrote a paper in 2007 talking about the girth. And remember my talk, I want to know connection between graph properties and ring theory. So here is one result, kind of nice. If you have a reduced commutative ring, what we mean reduced? 0 is the only nilpotent element. That means x to the n equals 0. That means x has to be 0. That's it. That's what we mean with reduced. If your ring is reduced, if you know that the girth of the zero divisor graph is 4, then I know the structure of the ring. It tell me number B, it tell me my ring R is a subring of a product of two integral domain. Well, if your ring R is a subring of the product of two integral domain, so what will be the total quotient ring? Remember, the total quotient ring of R is R localized at the set of all uh, regular element. What I mean with regular element, they are not zero divisor. Like you take your set, let's call it F, equal all the elements of R, take away the set of the zero divisor. These we call them regular element. If you do R localize at F, this is the total quotient ring. This is like, the Q and Z. A Q is the quotient field of Z. Anyway, so I know what is my ring, or at least I know what is the quotient field of the ring. But if the quotient field of the ring is F1 product F2, where F1 and F2 are a field, then, and they did the same thing when the set of nil are non-zero. So if the girth is 4, they tell you what does the ring look like. And this is the kind of relation I am interested in. It's a graph property, and at the same time, I get some image or picture on how my ring should look like. This is very, very beautiful. For me, my personal opinion, the connection between the graph and the ring. One of them, like if you give me this ring, like B, then I know what is the girth of the zero divisor graph. If I know the girth, then I know how the ring look like. Okay? All right, and so on. I think I have maybe 5. How many minutes left for me?
5-10 minutes, sir.
Okay, so I will move on. In the same paper, because remember that the girth is either 3 or 4 or infinity. For number 4, they consider the ring when R is reduced and non-reduced. What about infinity? They did the same thing. If your ring is reduced, meaning, 0 is the only nilpotent element, then the following are equivalent. Okay, the girth of the zero divisor is infinity. It tells me again about the structure of the total quotient ring. Okay, and the same thing for non-reduced. When the nil of R, the set of all nilpotent element, is non-zero, then I know how the ring look like. Okay, here is a good question. We know, what complete mean? KM, meaning complete, meaning every two vertices are connected by an edge. Usually complete graph, we write K index by M, where M is number of vertices. So if your graph, the zero divisor graph, is complete, what can I say about the polynomial ring? This is Rx, polynomials with coefficient from R. Is it complete? The answer is no. So you could have a ring R where the zero divisor graph is complete, but this is not complete, the polynomial ring, the zero divisor. And here is the example. You take the ring Z2 cross Z2. Then definitely the zero divisor graph of this ring consists of how many? Two vertices. So the zero divisor graph will be K11, right? But the polynomial ring, the zero divisor of the polynomial ring is not. Like you take A to be this vertex and B this vertex. And then when you do multiply them, you don't get 0, because complete mean there should be an edge between every two vertices. Okay? All right. Well, remember what this means. This is the power series when you have double bracket. And remember, we always think of the polynomial ring as a subring of the formal power series. So if the polynomial ring is not uh, complete, then definitely the power series is not. Okay, what is the okay, I want to move to another graphic quickly because there is a result there that strike me. The annihilator graph. What is the annihilator graph? The annihilator graph introduced in 2014 by Ayman Badawi, and it's defined to be, the same thing. Uh, the vertices will be the non-zero zero divisor, and if you have two vertices, they will be connected if the annihilator of xy not equal the annihilator of x union the annihilator of y. The annihilator of the product of two vertices is not equal to the union of the annihilator for each. Okay? And this annihilator graph, the zero divisor graph, will be a subgraph of this. So what are the properties of this graph? Here are the properties for any commutative ring. The annihilator graph is always connected. Diameter is very small, less or equal to 2. Here is an interesting number 2. If your ring is reduced, then the annihilator graph will be exactly the zero divisor graph if and only if R has exactly two distinct minimal prime ideal. And as I told you, this is the kind of properties I always look for. Like the annihilator graph is identical. Okay, can you tell me something about the ring? I tell you, yeah. Your ring has exactly two distinct minimal prime ideal, and vice versa. If you have a ring with two distinct minimal prime ideal, then these two graphs will be identical. Okay? And here are some properties you can read, but please keep in mind this result is given for reduced ring when they are equal. Why? Because they're going to end up. So like this ring here quickly, this ring has three minimal prime ideal. So you don't have to draw the graph. You know, they are not equal because this ring is reduced. That means 0 is the only nilpotent element and has three minimal prime ideal. So that means if you try to draw these graph, they are cannot be isomorphic or identical because they should have. Okay, anyway, you're gonna tell me what this has to do, and there is something connection amazing. In 2007, I defined two absorbing ideal. What is a two absorbing ideal? If you have an ideal I, then I is called two absorbing if whenever a product of three elements in I, then AB in I or AC. So this is like generalization of a prime ideal. Because in a prime ideal, if you have a product of two in I, then one of them has to be in I. So a generalization of this is what we call two absorbing. If you have three elements in I, then a product of two will be in I. Okay? And what this has to do with the graph. I was amazed when I saw this result in 2018. A complete answer to a question on a graph. by also they are Iranian mathematician. In 2018, they gave that the annihilator graph is the same as the zero divisor graph if and only if 0 is two absorbing ideal of R. Wow, that's a very beautiful result. Every time I come across this result, I get excited because I never thought how this two absorbing ideal related to kind of a graph. And here they give a very simple. Remember, I have an answer to when they are identical, when the ring is reduced. And I said they should have two minimal prime ideal. But I don't have an answer in general. Or maybe if I do, then it will be like 3, 4 conditions, maybe. But that's it, simple condition. That's 0, okay? All right, I think I should stop, and I thank the speaker, and thank you for coming, and I wish all best. Okay, I stop here.
Thank you, sir. Any questions from the audience?